check, check. Check, check, check. Sound check.
So, good morning, everybody. I have the pleasure to present the early Gaia data release, the early installment of this data release. I'm here at the Geneva University premises in Ecosia with the help of Krzysztof Nienartowicz, who will help me to do this presentation.
Enjoy and let us know in the comments how's it going.
So I will start. The length of the event will be about 1 hour. Okay. A bit too slow. So as a foreword, today is for us an exceptional day. It is this data release event which consists of new photometry, so positions for many stars, and also new photometry, which consists of brightness and colors. This solution is based on 34 months of data taken by the Gaia spacecraft and calibrated by the Gaia consortium. A little hiccup. Okay. So the plan of the talk, I will present once again at the observatory at the University of Geneva, the Gaia in a few minutes. Then I will speak about the two past releases, DR1, DR2, and this early installment of DR3. I will then go to some results on the scientific verification articles. Then I will go to the Gaia archive to see how we can extract data from the archive. I will have a few words on the consortium, and after I will speak about the DR3, DR4, and DR5 data release, which will happen in the future. And then we will go to conclusions. So first, Gaia in a nutshell. So Gaia is really a survey machine. It is a cornerstone mission of the European Space Agency. It is observing all objects brighter than a certain limit. Gaia is observing about 2 billion objects. The measurement of Gaia consists of positions, that is astrometry, brightness and colors, this is photometry and spectrophotometry, and also radial velocities with a spectrometer for more than 100 million objects. Gaia was launched by a Soyuz rocket in December 19th, 2013, and it will last, we hope, 10 years. And during these 10 years, it will observe the whole sky repeatedly. There will be 140 times, 140 measurements in each 9 CCDs for the G-band, the astrometry and the BP-RP CCDs, and also 80 times in radial velocity spectrometer. So why Gaia is so extraordinary? Why is it a real fest now, a big joy? This is because really Gaia is an exceptional mission. First, it measures all the entire celestial sphere, all the objects, southwest, north, east, and this is because it is in space and can have access to the whole sky. And in this space platform, which is the Gaia spacecraft, there are several instruments. And there is another aspect there that you have in these several instruments nearly simultaneous measurements of all these instruments. This is also quite unique. Then it has an enormous dynamical range. It's going from magnitude 4, so very bright objects, to magnitude 21, and with a uniform, or nearly uniform, photometry and astrometry. Then, as we already said, it's measuring 2 billion objects. So there is a large number of sources for this photometry and astrometry all over the sky. Then it is multi-epoch, so the measurements of one object is repeated. We said for 10 years it will be around 140 times. It produces, when the data is correctly reduced, a 2D map, which is unprecedented in the positions. Gaia gives also depth to space, because with the parallax, with these astrometric measurements, you can determine the distance to the object to a precision, again, which is unprecedented for such a large number of stars. Gaia gives also motion to stars, again in an unprecedented way. And Gaia gives characteristics. So we have a real census. It's just not the motion of the stars, it's also the characteristic of each of the measured stars. So there are astrophysical parameters, there is information about variability and about binarity. And finally, Gaia is a fully European project, a space project. I think there also Europe has a lead. A few years ago, Uli Bastian had a good idea for a name for a group. It was called ELSA. It's leadership, European leadership in space astrometry. And there is no equivalent in other space missions from other countries. So for all these reasons, Gaia is really, really a unique mission. So a quick reminder about the history of Gaia. As I said, it was launched in 2013 from French Guyana on a Soyuz rocket. It is located in the Lagrangian L2 point. It seems now that many good missions of Gaia, of ESA and NASA are located there. It's like a parking lot of very good missions of ESA and NASA. And the way Gaia is functioning, it's a survey machine. It's continuously scanning the sky with a period of 6 hours. So there you have two fields of views, which are separated by 106.5 degrees, and it's scanning continuously the sky. So Gaia is functioning 24 hours per day, 7 days a week, 365 days a year. And so these two fields are projected on the same focal plane, made of CCDs, and there the stars are passing. So here is an image of the focal plane. So first, you have the sky mapper here. You detect a star. There is something. So the satellite knows that it has to do, there is something bright enough. Then the satellite knows that it has to do something. And it is then going through this, and you do measurements. So this focal plane is about 1 billion pixels, and it's about this size, about half a meter height. And so what is happening there is that from L2, that's 1.5 million kilometers from Earth, you cannot transfer, because the integration time here is 4.4 seconds, you cannot transfer 1 billion pixels every 4.4 seconds. So what you do is, as we saw, you just take post-stamp images on each CCD, and you reduce what you have to transfer. And from that, you have, in fact, one transit. One such passage is a field of view transit. And the one difficulty of Gaia is that you observe something, and then 3 weeks later, you observe something which is around the same position. So is it the same star, or is the star moved because stars are moving, or is it an asteroid which is moving, or is it a variable stars which disappeared and another by chance just reappeared? So globally you have now something a bit less than 100 billion of these observations, and you should link all these observations to one source. It is a bit like a detective who is trying to find, he has murders on a map, and he's trying to find the serial killer. Okay, so this is really a data avalanche, and to make a long story short, you put a bunch of people, 400, more than 400 together, you work for 10 years or more, and then you get these data releases, which are which are made to the public, and then the astronomers, the amateur astronomers, can use these data to do further investigations. And today, as you probably know, it's the EDR3, a very special day. So the two past releases and this EDR3 release. So if we just say about the evolution, so globally, the good principle, the more you have data to analyze, the better you get in the different estimations of the data. More data is better estimations of the photometry, of the position and parallax, and on the proper motion. So globally, the photometry is going like it's proportional to 1 over the square root of the mission length. The same for the position and parallaxes. But for the proper motion, you go like 1 over the mission length times the square root. So with the proper motion, the longer you wait, the better it is. It is how, for example, the ancient Greeks, when you compared data from ancient Greeks and then more recent data, you have a very long baseline, and you don't need so precise measurement to have the measurement of the proper motion. Obviously, this is not only what is happening, that you add data and it is improving. You have also, people are working very hard to improve the calibration, to detect problems, so that you have lower systematic errors. You have also, as I explained earlier, every time a better source list, because you match better the different transits, the field of view transits, with to which source it belongs. And also, along the different data releases, you have more diverse products, as we will see. So the table of progression of the different Gaia data release. You have the DR1, DR2, and EDR3. So these happen every 2 years. And the data length that was used is 14 months, 22 months, and now 34 months. The number of sources with the position of brightness was going in DR1 from 1.1 billion, and now we are at 1.8 billion objects. The number of sources with G, color, parallax, and proper motion, you didn't have all this information in DR1, but in DR2 you had 1.3 billion, and now you have 1.5 billion. So these jumps, it's already from 1.3 to 1.5 billion, it's an enormous gain of number of sources. In terms of radial velocities, in DR2 there was 7 million sources, and in EDR3, to ease the analysis of the data, it's just replicated from DR2, except that a number of sources have been cleaned. There has been spurious sources, and then they have been cleaned in EDR3. So Gaia DR2 is an enormous success. And so it's always difficult to see on what do you measure this success. So here I took the citations. Obviously, that's one indicator. It's not an absolute indicator. But you can ask you, DR2 was published in 2018. You look how many articles have been published during 2018. You see that you have in astronomy on ADS 64,000 articles. And now you can use ADS and sort the articles, and you ask yourself which article is the most cited. So you see, if I prepare this slide, you probably guessed the answer. Globally, this is the summary of the content of the survey properties of the DR2 article. So this shows that Gaia is, it's an indicator that Gaia is really extremely used among the astronomical community. But it's not, yes, so the number of citations is nearly 4,000 citations. But it's not the only indicator of citation. If you look at the 5 most cited articles, in fact, 3 are directly related to Gaia. So this is for the year 2018. So it shows the enormous impact that such a mission, that Gaia mission has on astronomy. Now, if we look at the improvement between DR1, DR2, and EDR3, here is, in fact, the magnitude. So you have faint objects, bright objects, and here we plot the parallax precision. It is in logarithmic scale. And the different colors here indicate the different uncertainties that are reached. Obviously, when you have faint objects, the precision you get is less good, and when it is improving, and then in Gaia, you start to saturate the objects. There is a system which allows to deal with that, but it's more complicated. So there, at very bright objects, you have more difficulties to calibrate all this. And so what do you see? You have DR1 is up there. It's not, that was not that good, but at that time we found this already exceptional. And now DR2 is here in blue, and EDR3 is in green. And these lines are the future DR4 and DR5 extrapolated, and you see that it's theoretical, it's a straight line. What you should retain here is that from DR2 to EDR3, there is about a 30% improvement. For those who knows also about the offset of the parallax, we are going from an offset from 29 microarcsecond to 17 microarcsecond. So there is a global improvement of this offset, which is based there by the same method, looking at the quasars very far away object to calibrate these offsets. Now, some words about the Gaia parallax precision, because, yes, I will go back. When you look at, okay, 10 microarcsecond in parallax, or something like in position, what does it represent? So probably even many astronomers, they don't have a representation, even myself. What does it mean? It's like a very tiny quantity, but, and so to give this, what is the angular size of about 10 microarcsecond? So now this was something done by a slide by Barry Hall, one of our colleagues here in Geneva. And obviously he put a Swiss flag. This is the surface of the moon. He put a Swiss flag. When he was in Sweden, he put a Swedish flag. But we are in Switzerland. And so globally you have a person there. And so globally the size of a person seen from Earth, a person who is on the moon, is about 100 microarcsecond. And if you have a coin of 1 Swiss franc, so one euro, you have 12 microarc seconds. So globally, it's mind-boggling, the tininess of these angles that Gaia can measure. So remind that 10 microarc second is a really tiny, tiny angular resolution. Okay, so that was for the parallax. For the proper motion, so things are moving away. And this is again the same diagram where you have the G magnitude and the uncertainty on the proper motion, also in logarithmic scale. And you have exactly the same color code that you have EDR3 in green and DR2 in blue. Okay. What is to be retained there, because of the dependence of the mission length to the proper motion, you have not a 30% improvement there, but you have a factor 2. So really to measure longer is really improving the situation with the proper motion. Now, if you look at the photometry, so I did a little diagram where I thought, okay, I will plot 500,000 of the source with the highest number of measurements. So before, in the previous diagram, you were seeing lines, very nice lines, but often you see something like this. So the line represents this, this part of the diagram. So what do you see there? You have the mean magnitude and you have the uncertainty on the mean. So you see that already in DR1 you reach below the millimag level, but for a relatively small magnitude interval. And here you have, up there, what you have is variable stars, but also mistakes and problems in the photometry. Now, if you go to DR2, so DR1, DR2, okay, you see the improvements. What you see also that you have this feature which is dealing with the beginning of saturation and problems. Okay, you work and you really reduce these effects. And now DR2, EDR3. Okay, again you push down the data, and also these regions are improved. So with the next data release, there the bright part will be improved a lot. Okay, what can you do with all this data? So this is the content of the data release. What can you do? You can do a flux map of that is an height of projection, and you can see the Magellanic Clouds here. We will come back a bit later. You have the plane of the Milky Way. We are in the Milky Way, so that's like seeing the forest from inside. And you have this obscuration, which is interstellar matter. And so this is a map in flux. You can go also to the map of points, density map. So what do you see? Okay, this was for DR1. Ooh. Then you have you can see very clearly the pattern of the scanning laws. You have stripes, and this is how Gaia is scanning the sky continuously, but with some irregularity. And so now, if we jump directly to EDR3, you have this. You still see some pattern, but they are a lot diminished. And obviously, this pattern will improve and improve again. Okay? What you can do is also, you can think, okay, you take this map and you take the stars, the displacement of stars, the proper motion. And so this is a displacement which is shown of 1.6 million years. And so one star, pop, is a straight line. So you have some stars which are moving like crazy here. So they are going extremely fast, high proper motion stars. What you can do, so this is the previous things were a bit like showcase of Gaia, what are the improvements of the data. And now you can go a bit further in more scientific work. And here I show the period luminosity relation for Cepheids. So the Cepheids, they are standard candles. So if you know the period, then you know the luminosity, you observe the brightness, how bright they are from Earth, and you derive the distance. So it's like a light bulb, and you know how many watts they produce. So here in this diagram you have the period, it's logarithmic, you have 1 day, 10 days, 100 days over there. And you have here, we took the infrared absolute magnitude calibrated with Gaia parallax, and here it's Hipparcos parallax. So, okay, you look at this data. I often say here that it is when I started astronomy and I was trained as a physicist, and the people were showing such a cloud of points, and they were saying, oh, there is a relation. Okay, for me that was something extremely noisy. It was noise. Okay, now you go to DR1. There it starts to be more convincing that you have a kind of a slope. You see that the uncertainties are already large, but reduced from the previous slides. And then you go to DR2, and there you squeeze things. There you see that you have there is a relation between the period and the magnitude. And this is EDR3. So DR2, EDR3. And here you see very clearly in blue you have the overtone Cepheid, and there in red you have the fundamental mode. So clearly Gaia, here with this release and the future release, will allow to calibrate the different standard candles in an unprecedented way. Okay, now I will go to some scientific verification articles which are published along the data release. So in each data release, there is a certain number of topics which are touched, and people are working from the consortium, are working, and they are checking and looking if the data is up to the expectation, and also may detect some problems in it. So there are 4 articles. There is an article on a nearby sample. So globally, you look in a sphere around the sun, and you see what you can do with this. You have an article on the galactic anti-center. So you look opposite to the galactic center direction, to the outskirts of the Milky Way. You have an article on the structure and properties of the Magellanic Clouds. And you have also an article on the acceleration of the solar system from Gaia astrometry. Okay. So the first article is concerning the nearby stars. What do you see there? That globally the census of nearby stars is very, very poorly known without Gaia. So look at these numbers. If you have 10 parsec, a sphere of 10 parsec, you have only 400 stars. And there you can say you have different circles. In yellow you have Gaia catalog. In light orange you have Hipparcos, and ground-based observations are dark orange. So globally you see there for these 400 stars you have kind of match. You knew that these stars were in this 100 parsec. Now, if you go to 25 parsecs, you have 5,000 stars, and you see already that maybe half of the sample were not known. You had stars, globally you didn't know, and that's half of the sample of these 5,000 stars. You didn't know if they were inside the sphere or outside. And now if you go to 100 parsec, you have 300,000 stars, and you see that only 10% were known. to be inside this sphere. So there, just these very simple things, you remark that Gaia is doing an enormous contribution to the knowledge of solar neighborhood. Okay, I'm half of the middle of the talk. I think that's good. So now we will have an exploration of the 100 parsec. So there is a movie. And so what do we see? We have stars, and that's so real position of stars. And now we are going to certain region of this 100 parsec. So with you can people who are you can see also that there are the motions. So these are a bit random motions of the different stars. Some vectors which represent the motion are large, some other are small. Motion is small. And we can go there to some maybe special cases. You have, for example, sometimes two stars which are close to each other. So maybe they are bound together, maybe not. So here you have these two stars, and you look at the motion of these two yellow stars. And so what do you see? Oops, they move in the same direction. So this system, which is bound globally, is a real pair and is moving. Here is another pair of a double star. So it's very clear that they are not randomly oriented. This is Heidi's cluster, so a star which were born together 600 million years ago. And there also you can see what is the motion of these stars. So, you see that the motion is not that large and they all go in the same direction. So globally in the Milky Way, you have stars which were born in a certain location and they have all the same motion. We go to the Coma Berenice, it's Melot 111 cluster, and there again you will see that, there the proper motion of all these stars is really tiny. And it's embedded in many other stars that have very different velocities. Here is, so that's a view of the sphere of about 100 parsecs, and you have 330,000 stars. Okay, that was the first movie. Okay, and then you can take this, you have another movie, you can take this same sphere of stars, and you make it, you have a galactic model, and you make it evolve. You see that you have little spots there, over densities, they are clusters, and that's how the stars are moving in the Milky Way. And you have above, top right, the time it takes. So you are in millions of years, 200 million years there for a rotation. And you have the different view, top view, side view, and with a view with an angle. You can see also, if you look, you see that you have these stars which are moving in the galactic plane, but if you look later, we didn't see here so well, but you have on the movie, you have also stars which are in the halo and going through the galactic center. So among the small sphere we have, you have the very high very high velocity star. Usually they are from the halo of our galaxy. Okay. So this is about, in a way, the exploration and astrometry. And then you can also do, with the photometry, the formation of the HR diagram with another movie. We start from the burning sun. Our burning sun, it's very hot, 5,700 degrees. And we do a zoom out. And we see that there are not so many stars in the neighborhood. And then you can start to see stars. They are of different colors. The colors represent the different temperatures. Blue stars are very hot stars. Red stars are very cold stars. And here we do a little tour, and we take the 400 light years, which is 125 parsec. We select those stars, and then we are sorting them or ordering them by luminosity. Okay, that's bright stars are up, faint stars are down, and there we order by color, by temperature. And you have the fundamental diagram, Hertzsprung-Russell diagram, with this sample. And so this is the diagram that you have, HR diagram with the photometry, the G, and this is labeled here, G and GRP, to catch this faint tail and the absolute magnitude. So as I said, bright luminous stars are here, and low luminous stars are there, hot stars are here, faint stars are there. Here, what is in the article, what they do, they use machine learning techniques to separate some spurious data with good data. Because obviously, the point is that when you have nearly 2 billion stars, an exception, you have a tiny exception in the data, and you get thousands, even tens of thousands objects which are spurious. So that's, when you deal with big data, that's one of the problems. And so you have the orange points there, it's doubtful points, and the blue ones are good points. Now, a special focus of my interest, you have we just saw before, the white dwarf sequence. So the white dwarf sequence, here is the white dwarf sequence. Gaia revealed very interesting things in DR2, is that you have a sequence A, you have a sequence B, and you have the crystallization sequence, which was predicted theoretically decades ago. Never observed. Gaia was, with DR2, able to observe. What do we see here between DR2 and DR3? There has been a study by Gentile Fusio who published this catalog. Apparently, so that should be explored. Suddenly, you have many stars with a high probability that were not in the catalog of Gentile Fusio that are appearing here. So is it a mistake? Are these binaries just white dwarf binaries? We have to see. In fact, I'm doing a study with a student who is now in Vietnam, Tin Nguyen, and we are working on the variability of these objects, and obviously with EDR3 we will have to study this part of the diagram. Okay. Okay. Now we go, that was the first article on the nearby sample. Now this is the second article with the galactic anticenter. This is not our Milky Way. Again, we are in the Milky Way. This is another galaxy, but if we take it as a proxy of our galaxy, so what do you have is that you have the galactic center, you have the sun, which is not far away at 8 kiloparsec, and we look at the direction opposite to the galactic center. And so why this region? Why this region? Because it's you don't have much extinction in the anticenter, and you can, because the motion of the stars there, they have nearly zero radial velocity. So globally, the motion you have is determined fully by the astrometric solution. And so you can have properties, radial property, you can have motion velocities. So in this direction like this, it's v phi, and you have perpendicular vz direction, and you can study the motion of these stars. You have 21 million sources there with the selection that the author of this article studied. And so the anticenter is interesting because it is a meeting point of distinct components of the galaxy, the disk and the halo. It hosts ancient and recently disrupted stellar system of extragalactic origin, and it also shows signature of internal and external perturbation. So for these reasons, it is a very interesting sample. So I had to pick up some topics there. Yeah, okay. Is now, if you look at the distance with respect to the galactic center, we are at 8 kiloparsec, and you plot this motion in the galactic plane of v phi, and you see overdensities. So this is, you have some ridges, so some were known in the literature, and suddenly you see new ridges. So it can be, as I said earlier, some perturbation from external event or perturbation within our own galaxy. So that is a very nice result for the galactic anticenter. There are many more results in that paper. So now the third article is an article on the Magellanic Clouds. Here the astrometry, or otherwise the parallaxes, is not intervening directly. It's a property of the astrometry of detecting point sources and also properties of the photometry. So this is a reconstructed image with a different population of the large Magellanic Cloud. We see the bar, we have the, remember here, we have the impression of a bit of a rotation here, and we will see how with Gaia data it is revealed. Okay, you have, so this is, I remind, the third article on the Magellanic, this is the third article which focused on the Magellanic Cloud. And so here is the HR diagram you have. So that's labeled in BP minus RP and G. Here you can assume that all the stars are at the same distance, far away from the Magellanic Cloud. And so obviously the HR diagram you see is very different from the HR diagram we derived just before for the neighboring sample. So you can divide this HR diagram in different regions. You have young population, which is here, other young, three young populations. You have the red giant branch, the asymptotic giant branch, the blue loop, here region, and the Arar-Lyrae stars. And from that, you can see where are they located. And you see, for example, that you have many Arar-Lyraes which are in the galactic bar, but also all around, a bit like in the Milky Way, in fact. You have a young population. We see they are globally a bit all around. So that's pointing out that recently there were star formation happening in the Magellanic Clouds. And so you can use there the astrometry to have the motion of the Magellanic Cloud. And this is a beautiful diagram. You really see, so this is the average motion of the stars in the Magellanic Cloud. And you can see the velocity field of the Magellanic Cloud with EDR3 results. Really, you see there this galaxy neighboring galaxy from ours, which is rotating. You can also try to enhance enhance some contrast in the galaxy. And here is, you have the small Magellan Cloud and the large Magellan Cloud. And there they use the techniques to enhance, or method to enhance some overdensities. Because as we saw in the previous anticenter, you have overdensities which is related to the motion and also to the distance in the Milky Way. You have accreting event, perturbations, and there you have the same. So you have the southern and northern tidal arms, which were known here, but you see also a bit new overdensities. So we will see how real they are and why we have these overdensities in these two regions. This is now for the Magellan Cloud, some highlights I took. Now we can go to the fourth article. So this is the acceleration of the solar system from Gaia astrometry. So in the 18th century, when Bradley was trying to see the parallax motion, which is the fundamental reason why Gaia was put to space, Bradley fell first on a problem that it took 2 years to discover. That is, as the Earth is moving around the Sun, that we are in a heliocentric, not geocentric system, because you move, you have to, the stars move in, that's apparent motion. The stars are not where you expect them to be. So it's the parallel is that when it's raining and you have the umbrella, and now if you start to move, then you have to bend your umbrella not to get wet. So globally, you have to orientate the position of your telescope a bit differently because of the motion of the Earth around the Sun. And this Bradley's aberration is a direct proof that we are in a heliocentric system. Obviously, now, if you don't move at constant speed, but you move around with an acceleration, you accelerate or you turn, then you have to orientate your umbrella in a different manner. So very early, 19th century, John Pond, the Royal Astronomer in England, he realized this. So at his time, it was totally outside the capabilities, technical capabilities. And in fact, we are accelerating. We are turning also around the galaxy. So, as we said earlier, we are about at 8 kiloparsec from the galactic center. We have a speed of 200 kilometers per second, and we do a rotation in about 200 million years. And as we are rotating, we have an acceleration. And then you can put numbers. Several people put numbers. No, we can show the little movie of acceleration. So if you take the quasars, you have the quasars here, and you, is it running? Yes. And then what you see is that in principle, this effect is obviously not the true effect, it's a tiny effect, but globally you have an apparent motion of the quasars, which is due to the rotation around the galaxy. So we stop the movie. Okay. Okay, but in fact there has been estimation of this effect, and it's an extremely tiny, ridiculous small effect. The rough estimates done in the 1980s or 1990s, the acceleration effect is 2 × 10⁻⁻⁻⁻ meter per square seconds. And in fact, it corresponds to about 5 micro arc seconds per year of proper motion at maximum. So globally, this is really a tiny effect. And there, furthermore, when you look at the quasars, these objects are very faint. And so that's exactly where Gaia is the least performant. This effect was seen in radio VLBI, very long baseline interferometry, but never in it was never observed in optical. And now the result, which is quite astonishing. So you take a list of 1.6 million quasar-like extragalactic sources, you take the Gaia observations, and you do the processing of them, a bit complicated, and then what you get is that you have a measurement of 2.32 plus or minus 0.16, 10 power minus 10 meter per square second. And it corresponds to a proper motion, so the estimations were correct, of 5 micro arc second per year. The formal error is 0.3 micro arc second. So it's really a tiny, tiny effect, and Gaia is able to measure it with very extremely precise result. When we were presented this result, on my side, I could not believe it was true. It's really mind-boggling, I would say. And we believe that in the final data release, we will reach 0.1 micro arc second per year. So globally, we said that 10 micro arc second is a coin on the moon seen from Earth. So 0.1 is a lot smaller. I didn't do the calculation, unfortunately. I should have. Okay. Okay, so now we will go to the Gaia archive. I will a bit speed up, but so the Gaia archive, how to access Gaia data. You can have ESA from ESA. This is the link. You can query with EDQL queries. You have TAP, table access protocol, can be used from Python or Topcat, and you have partner data centers, Strasbourg, Heidelberg, Potsdam, and Rome. If you need any help in these queries or understanding something in Gaia data, you can contact the Geneva team, myself, or any CU7 DPCG team member. And in fact, we are the contact point for Switzerland. We receive semi-regularly, I would say, requests for clarification in Gaia data. We go to the consortium. So for the Gaia consortium, it's a group of 450 members. We are, many of the people are supported by many national funding institutions, and we must be very thankful to them. Also, people are very dedicated. Even recently, I was writing to the main author of the acceleration paper at past midnight, and I received a very long explanation. He was up on the deck, working on the data. So now we will go to the movie. A little message from Anthony Brown, who is the DPAC, the chair of the consortium.
Yes, of course, it was a difficult time since March, especially as we were already nearing the end of the data processing and preparing for Gaia EDR3, which we had originally targeted for September of 2020. But then the pandemic hit, and as for everyone, of course, this meant difficulties for working efficiently, especially for those of us with children or partners in critical jobs, etc. And so one of the first things we did is to try and lower the overall stress levels by telling people, hey, take care of your own well-being first. and then we'll worry about all the things that need to be done for DPAC. So that's also why we immediately decided to postpone the release without directly giving a target date. And I think this helped to keep everyone at least away from the worst of the stress. And I have to say, DPAC did really, the DPAC members did an absolutely amazing job in getting all this work done in these difficult circumstances to prepare Gaia EDR3 and be able to present that to you today.
The future, so the full DR3 will happen in 2022. There is unchanged source list, unchanged astrometry, unchanged photometry except a little correction. BPRP-RVS mean spectra will be available. Variable star catalog, non-single star catalog, solar system bodies catalog will be published. 30 million radial velocities, some radial velocities time series for variables, a few thousands, astrophysical parameters, and also a pencil beam with all the photometric time series in the direction of M31. That will be the output of DR3. The DR4 will consist of 66 months of data. It will give a full astrometry, photometric, astrometric, and radial velocity catalog, all available variable star and non-single star solutions, the source classification with astrophysical parameters, unresolved binaries, galaxies and quasars, an exoplanet list also. All epoch data will be available, astrometry and photometric time series. The mission extension, so now the ESA Science Program Committee for the spacecraft operation confirmed or extended up to end 2020. There is an indicative approval up to end of 2020. The hard limit is the propellant for the micro-propulsion system. The DR5, if approved by SPC and if spacecraft health allows, that's for 10 years of data, the improvement will be of 40% for the nominal mission and a factor 3 for the proper motion. And we go to conclusions. So, EDR3 and DR3 will surely be another landmark in astronomy. We wish good work for the future users of EDR3. If you use Gaia data, please read articles, documentation, and also a web page on known issues which will be updated. If you have any question, you can contact the Geneva team, contact point for Switzerland, and there is a lot more to come in the future data release. You have this web page which gives you, I think, in a few minutes, everything will be open. And you can even find, I believe, Lego, how to do a spacecraft in Lego in these pages. And so now we are 2 minutes. If we have time, we can answer some questions, or we are waiting a few minutes because there is a web page of ESA which is showing the connection at 12. So we have 1 minute.
There are questions on the editor. So, will the flux map be available as a high-resolution image for download?
So, will the flux map? Yes, the flux map, yes, it will be, it is available. So all material that I presented is available. I just showed before the web page of the data release, and in fact all the movies, all these maps will be available. Obviously, if the person wants to see a very specific region, then it can go to the archive and it can just download the data, do its own selection, own cleaning, and have the corresponding map.
What was the VLBI measurement precision? Is it Gaia better?
That I don't know. I have to see. So I guess it is maybe even in the introduction of the paper. In the paper there is a very nice historical introduction to this problem. Okay, so do you have the map on? It is on the map. And now you see the connection, people like crazy. I don't know what time it is in US.
6 a.m.
6 a.m. So people woke up. Oh yes, but
it depends on the where.
you have in California, you have it's 3 in the morning. So also in China, in Japan, in Australia, in South America. So just in less than 1 minute, there are many downloads. So this is already the first minutes, the system didn't collapse. This is very good. So there are many, many queries. So now to the... And now I think, next page. So thank you for your attention. And now I will take the sanitary precautions. We will have some real champagne. We are only 2. And we will have this. Careful. Last time I did this, I put this on the computer. So that was Pierre Dubat. He had to replace the keyboard. But this time we were...
And thanks a lot to everybody who helped us. And see you soon during DR3.
Full DR3.
Full DR3.
Cheers.
Cheers.